The last section of the course is on AI and deep learning, and we will start by motivating the problem. There are three main success stories behind the deep learning rise of the last years, and three main applications of deep learning today, which is image processing, natural language processing, and robotics. What is image processing? It's basically a machine learning algorithm that takes images as inputs, and those can be photos or sequences of images, which are videos, and the outputs are the labels associated with those images, for example, what type of objects are seen on the image. Natural language processing, you use natural language processing every time you try to dictate something to your cell phone, every time you use one of those translators like Google Translate, every time you talk to the automated support system in your bank, or when you purchase something from Amazon. And robotics is probably less visible to in daily life, but a lot of the things in warehouses in Amazon, for example, are roboticized. And probably the biggest next thing in the consumers market for robotics is self-driving cars. So you probably have heard about those. And essentially, deep learning is behind all of those three major applications and three major domains. What is deep learning essentially? Deep learning is just a pattern matching plus dimensionality reduction. And when you start talking to people who do data science and do statistical analysis, you'll often hear that, oh, deep learning is just a pattern matching, those models are not explainable, and they should not be really used in practice. This is true, they're not explainable, but it doesn't mean they shouldn't be used in practice. Essentially, deep learning model is used for prediction, and it can outperform any other known predictive model. We talked about three types of predictive models so far. We talked about the linear models. We talked about the logistic regression, which is just a generalization of the linear model. Remember, it's a linear model, and then we apply logistic function to the linear model. So essentially, this is pretty much the same. And the next type of model, we talked about tree models and the nearest neighbor models. So essentially, three types, 1, 2, 3 types of models we talked about, and tree models was the most powerful predictive model so far. And you will see that deep learning outperformed tree models in many of the tasks, including those three important tasks which we mentioned in the previous slide. So what is essentially pattern matching? Pattern matching is just a way to see a pattern without ability to explain this pattern. And here is a historical example of pattern matching for mammograms. That's how mammograms started being used for cancer prediction. A scientist who was looking at the sequence of mammograms realized that those mammograms that were taken from women with breast cancer would have a dense spot on those mammograms. And those dense spots will look like a white blob on the image. And just by observing many images, the rule was designed in the following way. If you see a white blob, then it's very likely that the person associated with this image has breast cancer. So white blob, meaning that cancer is likely. So that was the rule that was designed by just purely observing the pattern. And scientists didn't really know why cancer patients will have those white blobs, and it took several years of science and explaining those high density tissue formations and why they are associated with the cancer. But before we had science, we still had this predictive rule, and we were able to use this predictive rule very successfully and identify many of those cancer cases. So explanation often comes after the pattern was found, and pattern actually leads to new findings and new research and new explanations. But it doesn't mean that just purely pattern matching cannot be used in an efficient and useful way. And essentially, deep learning is doing very similar thing. Deep learning is predicting, doesn't doing pattern matching without really explaining things. And for a lot of the applications where deep learning is used, we don't have good explanations why it works, why it predicts what it predicts, but it doesn't mean that deep learning is useless and shouldn't be used for predictive tasks. It's actually quite opposite. Here is an example of pattern matching. The most powerful chess engine nowadays would use deep learning. Chess is the game with very large number of combinations, and the number of combinations called Shannon number, 10 to the power 152. And in the old days, the way that chess engines would be built, so old AI, and if you remember this Deep Blue machine, the machine that won against Kasparov. I think it was 1998 or 1999. You'll have to check. This machine used what is called a tree search. Tree search means you have a position on the board, and the machine has to make a move. And what machine is trying to do, it tries to analyze all possible moves. So all possible moves. And let's say a machine has 10 pieces, and each piece on average can have potentially 5 different moves. So you have 50 moves to be analyzed. But then what machine does, machine analyzes what happens after the first move. So after the first move, it analyzes the next possible move. And for this move, it does the same thing. And it keeps doing that. And essentially, you build this very wide and very deep tree of all possible moves, and machine is trying to do it up to 17 moves. But as you can imagine, the number of possible variations, so possible moves, when you try to plan 17 moves ahead is large. And machine was not able to process this large number of moves, so machine used what is called heuristics, or handcrafted rules. So this tree search was combined with handcrafted rules. And the handcrafted rules were mainly designed by grandmasters, by chess experts. What they would do, they would have a large table of those rules, and rule would say, if you try to move a queen, you don't move a queen to where it can be taken, for example. So that's the very simple one. But there are more sophisticated rules of that sort. So essentially, the machine was able to avoid moving along some of those branches by using those shortcuts, by using those handcrafted rules. So it will eliminate some of the branches and will not move along those. That's called truncation. So this ability to truncate using handcrafted rule allowed old type Deep Blue machine to win, the world champion those days. So new AI doesn't do any of that. It essentially uses deep learning as the set of rules. And those set of rules will be learned from the games themselves. Modern chess engines don't have to ask chess experts, don't have to take those human written rules as an input. They all learn from the games, and they essentially use neural networks to learn those rules. We'll talk about this a little bit later. But let's go back to the problems that are mainly solved by the deep learning models nowadays. So image processing, essentially you take a set of pixels as an input. And what is an image? Image is just a matrix. It's just a matrix. And each pixel is an element in this matrix. And each pixel is given by the number 2 to 252, which basically shows the intensity of the color. And if it's a colored image, you'll have 3 of those matrices, one for red, green, and blue. So 1 megapixel image means that you have 1 million inputs, and if you have 3 colors, you have 3 million inputs. So you have 3 million inputs. Now you should compare it to the types of the inputs that we did before. In our analysis, we used tabular data and would have probably the most 50 or 60 different predictors of inputs. Now you go to much higher dimensionality. You go to 3 million predictors, 3 million inputs, and this is just 1 megapixel image. Now, audio is the same thing. It's just the sequence of the sounds. Each sound is characterized by the frequency, and you have to take the sequence of the frequencies and convert them into a text. This is another example of language analysis is automated translation. You give a phrase in English, the outcome is the phrase in French, and Google Translate uses deep neural networks to do this translation. And another example of image analysis, you give an image, and instead of just saying what's on an image, you try to give a description of the image. So you have to be a little bit more evolved compared to just labeling that as a child with a teddy bear. All right. So what, and that's essentially why do we care about deep learning. Deep learning solves those high dimensional problems. It uses very complex rules, so very complex models to go from inputs to outputs. Here are some examples of the number of the parameters. You remember in the linear model, we have the same number of parameters as we have features. So we have 20 inputs, we'll have 21 coefficients beta. In neural networks, you have much more parameters than inputs. For example, Google Translation algorithm uses 1 to 2 billion parameters. Alexa speech recognition would use 100 million parameters. And the Google Waymo, we don't talk about the number of parameters, but Google Waymo processes 6 gigabytes of data per second. So it's a very high dimensional data set. Google Waymo mostly uses images for perception and data from the LiDAR, which is also a high dimensional object. A large amount of those objects come to the Google Waymo algorithm every second, and they need to be analyzed quickly, efficiently, and that's how Google Waymo does what is called perception. Perception means the self-driving car tries to identify what happens around. Here is how neural networks work, or deep learning work. Essentially, if you imagine an image, a very high dimensional object, so you have 3 million inputs. What neural network tries to do, it tries to convert it into a set of features. And those set of features are going to be of much lower dimensionality. Say it's going to be 200 of them. So it takes this 3 million dimensional object and essentially compresses it to a vector that has only 200 inputs. And then it uses this for prediction. Here's a very high-level example of how this works. Let's say we have inputs associated with a property: size of the house, number of the bedroom, zip code, and wealth. And then what we try to find those features, or latent factors also they called. And essentially we're going to go from 4-dimensional input to a 3-dimensional input. And in the 3-dimensional input, we're going to combine those two into one feature, which is family size. Essentially, if you know the family size, you'll have a good idea about the number of the bedrooms and the size of the house. And we're going to also have this feature which is called commute or walkability. And if you know what's commute or walkability, you will probably be able to identify what's the zip code associated with this area. And also school quality. School quality will be associated with the wealth, meaning that the house is going to be more expensive in this area, the taxes are higher, the school will have more funding, and also the zip code. And then if we want to do a predictive model, we're just going to use those factors or those features to predict the price of the house. So that's the idea of those features or latent factors. And essentially, that's what deep learning does. Deep learning takes this high-dimensional object and then boils it down to those low-dimensional feature vector and then uses the prediction. And at the end, you can basically, once you have this 200-dimensional vector, you can use linear model here or logistic regression. So at the end, it's going to be the same type of model that you're familiar with, logistic regression for classification, if your y is 0, 1, and linear model for regression. So to summarize, the idea of deep learning is that you do dimensionality reduction. You compress the high-dimensional object into something that is manageable. So it's dimensionality reduction. And then you use a predictive model that you're familiar with, plus linear model or generalized linear model, like logistic regression. That's it. It just adds one more step to this task of prediction, doing this dimensionality reduction.